Hello, welcome back to our machine learning course. I'm Joaquin van Schooyen, and today we'll dive into the exciting world of Bayesian learning, which are models that inherently take into account that the world around us, that the data is uncertain, and will take it into account when making predictions. So it can tell you how certain it is about any predictions it makes. To get you in the right mindset, this is an interesting comic by XKCD. So here you have two people who are observing a machine that is built to detect whether the sun has exploded. It's night, so we can't see the sun, but this machine measures neutrinos and based on that can predict whether the sun has exploded or not. However, this machine has a 1 in 12 or 1 in 36 chance of lying to you. So it rolls two dice. If both come up 6, then it will lie, to not give you the right answer. Just inherently what it does. Now, you make one observation, and the machine says, yes, the sun has exploded. Now, there's two ways of looking at that. So, if you look at it in a frequentist way, it means that, well, there's only a 1 in 36 chance that the machine is lying. So, by that reasoning, the chance is 1 over 36, which is very small. And since that p-value is below 0.05, you can conclude that the sun has exploded. Right? The chance that the machine has lied is very small, so I'm going to assume that the machine has not lied. Right? This is one way of looking at it. Another approach is to take into account that there are other options that are even less likely. Right? So in this case, well, there's a small chance the machine has lied, but the fact that, the sun has exploded is much smaller than that. Right? So there's two different ways of looking at that problem. It's a common fallacy, and this is, of course, a hyperbole. It's people don't really think this way. It's just a representation of looking at the data in a different way. You can actually do some computations about this, and for that we can use Bayes' rule. So Bayes' rule basically computes what's called the posterior probability of an hypothesis or a class given some data, right? So the posterior probability tells you how likely it is to make an observation. So in this case, C could be the sun has exploded, given an observation. So X could be the observation that the machine says yes. Right? Now, to compute this, Bayes' rule tells you how to do that. It says the probability of a class C here, given data X, is, you flip it around, is probability of X given C, right? So you flip this around. That's the likelihood, the probability of making this observation given that the class is C. Right? So I'll give an example in a minute. Times the probability. What's the probability that class C occurs at all? Normalized by the probability of the data of the marginal likelihood. You don't need to take too much. This is basically just a normalizer. This makes sure that whatever is computed here is nicely between 0 and 1. Right? That's the main reason for the denominator here. Right. That's Bayes' rule. Let's try to apply this to our example. So we want to know what the chance is, the probability that the sun has exploded, given that the machine tells me yes. Right? So expanding Bayes' rule, I need to compute the probability that the machine says yes if the sun has exploded, the probability that the sun has exploded at all, and the probability that the machine says yes. Okay, how can we compute this? What's the probability that the machine says yes if the sun has exploded? Well, there's only 1 in 36 chance that the machine has exploded, so this chance is basically 35 over 36, right? Or 1 minus probability of a lie. Okay. The chance that the probability the sun has exploded, well, how do you compute that? Well, there's no easy way to do that, but you can, for instance, assume that the sun has an estimated life, well, we know that the sun has an estimated lifespan of 10 billion years. And so saying that this machine gives you an observation every hour or so, the chance that it explodes at any given observation actually is 1 over, well, it's 10 to the minus 13, which is really, really small. Right, so that's our prior. So we plug that in here. And then we have the normalizer, which, well, is basically the chance that the machine tells the truth and the sun has exploded, plus the probability that the machine has lied and the sun has not exploded. Right? Okay, now if you fill that in, you'll find that the probability that the sun has exploded, given the machine says yes, is actually 10 to the minus 12. So that's still very, very small. Right? And the reason for that is that we started with a prior which was already pretty small. Making this one observation or this one prediction by the machine that the sun exploded increases the probability. So it goes up from 10 to the minus 13 to 10 to the minus 12. It's about 10 times more likely now that the sun has exploded than before we made the observation, but it's still pretty damn small. However, if that machine would give you multiple times the answer yes, then this posterior after multiple observations would increase. Right? We can also take a more temporary. We're now under lockdown, right? So let's look at COVID and what would it mean if we do a COVID test that says yes. So we do a COVID test, and this test is 96% accurate. And so we want to know what the probability is of having COVID if this test returns positive. Right? And we have to assume a false positive rate, and for this example, you can assume a false positive rate of 4%. Okay, what's the prior? Well, the probability of having COVID, assuming that I don't know where you're from, so you're just one of the 7.9 billion people on the planet, and we know that there are currently about 117 million cases, then that probability is 1.5%, which is still amazingly high. That's our prior. Okay, what's the probability of a true positive? Well, that's probability of positive given that you have COVID. That's our 96% accurate test. The probability of a false positive is, as we said, 4%. This does not have to add up to 1, by the way. Right? Okay. Now, if a test is positive, let's see what the probability is. The probability that we have COVID given a positive test is the probability that we have positive test given COVID. That is 96%. The probability of having COVID, that's 1.5%. And times the chance that you have a positive test, that's the normalizer. If you compute this, you'll find that having only one positive test gives you a probability of having COVID of about 27%, which seems low, right? So the reason for that is that, again, it's our prior. You have a priori, before we do a test and before I know where you're from, you only have a 1.5% chance of having COVID. Having one positive test increases that from 1.5% to 27%, which is a pretty significant increase. But it's still not like near 100% likely that you have COVID now after one test. If, however, you do a second test, what happens? Well, if I know that this is the posterior probability after doing one test, then now, before you do the second test, your prior probability of having COVID is going to be 27%. Because I know that you had a previous test that's positive, my prior is now going to say 27%. Right? If I then recompute this, you will find that the probability increases to 90%. So having two positive tests will tell me that you have a 90% chance of having COVID. Again, having a third test will again increase it more and more. Also, this prior here assumes that I don't know where you're from. If I know that you're from a country where there is a COVID outbreak, this number will massively increase, right? And so that will also mean that this posterior probability will also be larger. Okay, I hope that gives you a good indication of what Bayes' rule does. So now we want to use that to build Bayesian models. So Bayesian models are very different from what we've seen before. And because they learn the joint distribution of the inputs and the outputs, right? So it looks a bit like this. So I have my inputs and I have my outputs. And I'm going to learn a joint distribution here. And by the way, this is going to be a Gaussian. We'll explain why in a minute. We're going to assume that the data is Gaussian distributed. Is it reasonable to assume that? Well, I'll get back to that, but it turns out that this is in fact reasonable. Okay, we'll deduce that. So for now, assume that the data is Gaussian distributed. So it looks a bit like this bump here. Right? If you look at the contours, it looks like this, right? So this is the probability of something this is probability density. So this is the probability of a certain outcome given some inputs and some outputs. Right? It's a joint distribution we learn. So what does that mean? So if you now look at the black lines, right? So if I choose an input value x, just clean this up. Okay, if I choose an input value x, you can see this blue line here is moving, right? So I learned this joint distribution from the data, right? So I've already learned this. Now I want to make predictions. So say that I give you an input like x is -1. What it tells me about the output is that, well, it will be around this value here. It will be around 1.5. Right? So if our input x is -1, our output is going to be a distribution. Right? It's a Gaussian distribution, a 1D Gaussian distribution around some mean, which is probably 1.5-ish. Or 1, yeah. Oh, it's actually 1. Oh, yeah, okay, sorry, yeah. So it's 1. So if x is -1, the output y is going to be a distribution around 1 and with a certain standard deviation, depending on what this joint distribution looks like, right? So that's nice, right? So already we see we get something extra. So given input, we don't just get one output prediction, we get a distribution, we get a mean and some uncertainty around that mean. So it tells me y is somewhere in the distribution, most likely somewhere near the mean. Another interesting property is that for any desired output y, so say I want y to be 2, for instance, or let's take 1.5. So say that I want y to be 1.5, well, then the input should be somewhere sampled from here, which is around -2-ish, right? Minus 1.5 again, sorry. Yeah, so say that I want this certain output, then now I know I have to sample x from this distribution. So any point I sample from the distribution will give me a likely output of y equals 1.5. Right. That's pretty cool, right? So not only can I get probabilities about a certain output, I can also assume a certain output, and then this will tell me what the input would be. Right. And this is also easily updatable with new data, as we saw later. So we can use Bayes rules. So say this is my my prior or a posterior learned from previous data. If I now get a new data point, I can update this distribution. And then, well, the previous posterior, so this distribution becomes our prior, and then after seeing the new point, we get a new posterior. These are all very interesting properties of Bayesian models. So, in other words, Bayesian models are generative, which is different from before. Like many models we saw before are discriminative. They tell you whether you are in the blue class or the red class. A generative model learns distribution over all the red points and all the blue points. So if I want another red point, I can sample from the distribution and get another red point. Or I can sample from this distribution and get another blue point. Right. And this is very powerful because now I can, after I learn the distribution of a certain thing, I can now generate more of that thing, right? So say that I learn the distribution of what human faces look like, I can now generate new human faces, right? And this is actually done in generative neural networks like GANs. This can actually produce very accurate images given a certain required outcome. Right? And same for text as well. That's a very powerful thing. So we'll get back to GANs in another course, not this one.